evening, ma'am.
Good evening.
Ma'am, shall we start our session?
Yeah, please.
Yeah. On behalf of R.M.D. Engineering College and my own behalf, I welcome Professor from IIIT. Professor Binsu, ma'am. She is professor in IIIT, and she is going to deliver the session 2. Topic is Introduction to Neuromorphic Circuits and its Applications in Healthcare Domain. Now I invite Srinidhi to introduce the guest to our forum. Over to Srinidhi.
Good evening, everyone. It gives me a great pleasure to introduce Professor Binsu J. Kailath, an eminent academician and researcher in the field of electronics and communication engineering. She currently serves as a professor and dean in the Department of ECE at the IIITM Kancheepuram. Professor Binsu completed her PhD in ultra-thin oxide MOS devices and MTech in microelectronics and VLSI design from the prestigious IIT Madras, and she earned his BTech in Electronics and Communication Engineering in the University of Calcutta. With over 2 decades of teaching and research experience, including 8 years at the College of Engineering, Chenganur, and since 2008 at IIITM Kancheepuram, Professor Binsu had made remarkable contributions to both academia and research. Her research interests span across cutting edge domains such as spiking neural networks, non-violent memory based in memory computing, neuromorphic circuits for healthcare applications, mixed signal IC design, and microelectronics and MEMS. Today, she will be sharing her insights on machine learning algorithms for design efficiency. We warmly welcome you, ma'am. The session is over to you. Thank you, ma'am.
Thank you, Ms. Srinidhi, for the nice words. I just want to add a line. I would not be talking on machine learning. Rather, I would be talking on, the spiking neural networks, spiking neuron models, and their applications. So basically, neuromorphic circuits and their applications for biosignal processing or detection of anomalies in biosignal processing. So shall I share the screen? So I hope the screen is visible.
No, ma'am.
Is it visible now?
Yes, ma'am. It's visible now.
Yeah. Good evening, everyone. So I'll be talking about neuromorphic circuits for detection of abnormalities in biological signals. When I say biomedical signal, we work on ECG. As of now, we work on ECG and EEG signals. So what we do is we try to encode the ECG and EEG signals using spiking neurons, basically the adaptive exponential neuron or Izikevich neuron and LIF neuron as well. And they extract the primary timing features of ECG and EEG from the encoded spikes. And then to evaluate the secondary timing parameters of these to identify different cases of ventricular and atrial arrhythmias, as well as to identify the status, to extract the statistical parameters from the primary timing characteristics of the EEG signal from the interspike interval, I mean from the encoded spikes, to identify particular stage of sleep, and develop ANN or SNN models on open source platforms to classify arrhythmias from these features, and also to develop an FPGA and ASIC model for ECG-EEG signal characterization system. To apply this technique to recorded EEG from control subjects without any neurological or sleep disorder and subjects in neurointensive care unit with different levels of drowsiness to identify the stages of sleep in neural ICUs. Now, coming to the system level design, the low power analog ADEX neuron as biphasic encoder has been used in ECG, EEG, and we can use the extract a specific timing information from this, and the FPGA ADEX prototype is to be developed. So this is an overview of the proposed system with respect to ECG as well as EEG. So these two signals, So the ECG-EEG will be encoded with an ADEX neuron, and then the timing features will be extracted from them, and they will be applied to an SNN. So this is like a simulated model, and then we will apply this entire thing onto. I mean, we have applied to an FPGA and ASIC implementation. So coming to the ECG, those who have undergone any biomedical courses or have studied biology in +2 would be knowing this, that any ECG waveform from a 12 electrode ECG from the lead 2 gives PQRST and sometimes a U waveform, where P, R, T, and U are positive waves and Q and S are negative waves. For this particular signal, and the distance from R of one cycle to R of the other cycle is known as RR interval. And all of us know that the heart beats at the rate of 72 beats per minute. So that normally gives to the, even though we say that ideal value is 72, and normally the clinicians prescribe 60 to 100 beats per minute as a normal case. When the beat is below 60 beats per minute or above 100 beats per minute, that is considered to be abnormal. And when we convert this to time period, the nominal period of an average RR interval value for a healthy person is around 600 to 1200 milliseconds, so or 1000. So approximately the beat every second you may have one beat, slightly less than 1 second. So that is how we find the beat. So this RR interval ideally represent a value close to 1 second. Few milliseconds, few means few 900, 700, 800, that range of milliseconds. So that is how we specify one primary parameter from the RR interval. Conventionally, what people do is they apply these frequency domain transformation techniques to extract these parameters. And now we can see that, as I said, 600 to 1200 as the RR interval normal value, and QRS means from the beginning of Q to the end of S, that is QRS, that is 80 to 120 milliseconds. And there are different kinds of beats which are causing abnormalities in the functionality of the heart. And these beats are classified as according to AMI standard, ARSV, and it will be classified as A if the RR interval is less than 600 millisecond and the P wave can be present or absent. QRS also should be less than 100 millisecond, and a beat will be classified as R type irrespective of the RR interval if the QRS width is greater than 100 millisecond, irrespective of presence of P. Whereas one beat will be classified as an S beat if lower RR interval followed by wider RR interval and the QRS width is less than 100 millisecond and P should be 1, means P wave should be present. And it is considered as V beat if lower RR interval followed by wider RR and the QRS is greater than 100 millisecond and the P wave is absent. So as you see, these are all the characteristics that are required to be identified in an ECG processing is in time domain, whereas conventionally people do frequency domain transformation. They take the ECG, apply frequency domain transformation, and then the spectrum will be, subjected to different types of analysis or machine learning techniques to extract the features, and from those features, the classifier would be operating. And because we realize that as these characteristic parameters are all in time domain, why don't we process the ECG in time domain? And that is how we came up with the system which will encode the ECG in time domain. So the property of a spiking neuron is that the spike rate, when I say spike rate, number of spikes or count of spikes per second, that depends upon the input amplitude, and that is a nonlinear relationship. It's not like, when you have 1 millivolt signal, if you get 10 spikes, and when it is increased to 2 milli, 3 milli, you get equal increment like 20 spikes, 30 spikes. It's not like that. As the input amplitude increases, the spike rate increase is non-linear, and based on the type of the spiking neuron, this non-linearity will change. So LIF, it is a linear process. Izikivich and ADEX, Izikivich follows a square root function, and ADEX follows an exponential function. So because the exponential function is found to be better due to many reasons that maybe in the slides to follow, we can see that we decided to encode the signal with ADEX. I mean, we have done comparison between ADEX and Izikivich, and we have published papers in that comparing all the 3 neurons for encoding these signals. So basically, most of the work has been done with encoding with ADEX neuron. So we this flowchart actually represents how we identify the RR interval. So as I said before, this R peak, the maximum amplitude of an ECG signal within a cycle happens at R peak. So as the amplitude of as the spike rate increases, as the input amplitude increases, spike rate in other words, it contributes to a distance between the spike being very less when the input amplitude is very high. So if you identify the ISI, which we call as interspike distance or interspike interval, if we can extract the interspike interval between the two spikes, and when that is the shortest, we can infer that corresponds to the R peak. And then if you have a positive spike, I mean the positive wave spikes, the shortest positive spike that comes before R for a positive wave will correspond to P wave, and the one after that will be T wave. Similarly, for two negative waves, if we get the shortest ISI, that will be Q, and before R, and after R will be S. So that is the basic logic how with which we try to identify the signals. But all these are good when the signal is exactly without any noise, without any baseline wander. Baseline wander mean getting shifted from the zero axis. So this is one example of an ECG signal. The topmost is the ECG signal. These are the spikes that is encoding the positive waves, and these are the spikes that are encoding the negative waves. So we can see that the signal which identify whether the presence of spike, which we can identify using a combination of asynchronous synchronous counters. We can easily determine whether the spikes are being received in the system. So we that particular signal identifies whether the spikes are received, and this is the example of the spike. We can see that this is what is known as the interspike interval, and the spikes are very close at the peak. So this is a zoomed version of the ECG, and this is the ISI values. And then the system actually identify different parameters, the RR interval, the QRS, and the QT interval with respect to time, and these are the parameters extracted by the system. And this is how the SC1 state of the channel meaning the neuron that encodes the positive wave, the negative wave, etc. So these are the signal that we have obtained. And then a comparison of the RR interval obtained from the proposed system and the MIT BIH system that has been compared here. We can see that the topmost red one is from MIT BIH and the system proposed, and we can see that the mean and standard deviation are very, very small compared to, and also the box plot also can be seen here, where also we can see that both of them, matches very much. And here comparison of RR interval obtained for another record. Why these records are important is, you can see the variation in the ECG signals are different in both the cases. So based on the characteristics of the ECG, whether the system is capable of extracting those parameters or identifying the PQRST waves. So that is important. So that is why we have applied different types of ECG signal. And here also we can see that the performance almost matches with that of the MITBH. And if we look at a particular V beat and SB rhythm, sinus bradycardia rhythm, we can see that the no1 represents the neuron out at the output, which is identifying the N beat as well as the V beat. We can see that the beats are identified by the system. And this is illustration of classification of the SB rhythm. We can see that this is SB and O3 gives SB. So we can, these pink spikes are output at the output of the SNN, showing that this is an SB system, SB rhythm. And then we also worked on SNN with a gradient-based backpropagation algorithm for ECG arrhythmia classification with the LIF as well as ADEX. ADEX is used to encode and LIF is used to create the SNN. Yeah, maybe I will skip this, this the need of the cardiovascular diseases. Yeah, these are some of the systems that are being previously implemented, energy efficient and robust SNN classifier with the LCADC sampled, and then training spiking neural network using lessons from deep learning. This also they have used for creating that. And then this is the LIF neuron model, and this is the ADEX neuron model. You can see that LIF has a single differential equation, first order, and ADEX also has a first order differential equation, but it is a combination of two equations are there because they are interlinked. And then this neuron has been implemented using a backpropagation algorithm given by this. Most of you working in this, machine learning algorithms or implementation of that, you can see that this have been, this particular algorithm have been used in many of the neural network applications. So what we have done is the lead to ECG, the feature extractor block are applied to the neurons, but this one we have not built the hardware. This is done in SNN Torch. SNN Torch is an online platform where you can simulate, where we can build and simulate spiking neural networks. So we have used a 3-layer SNN model compared with the two architectures, input layer with the 3 neuron, and then the hidden layer and output neuron with the 5, as well as 4 by n by 7. The hidden layer was a hyperparameter which we have varied during the simulation process. And we compared the performance of SNN1 and SNN2. We can see that both of them are, good. You can see the micro average pre-call, F1 score and recall, precision recall and F1 score are for SNN1 and SNN2 for LAF neuron and ADEX neuron. We can see that ADEX neuron performed much better than LAF neuron. And the proposed models compared with the compared with the state-of-the-art models with that comes in the literature. We can see that it has been compared with the different papers published, and we see that the architectures are, the very, very complex architectures they have, because they have 256 and then 641, then 153, and then 800, 640 fully connected, 15 layer. This FC represent fully connected. So the network is very, very complex, whereas ours is like a simple structure, fully connected, 15 hidden in the hidden and 10 in the hidden. For LIF, it was required to have 15, whereas ADEX only 10 neurons were enough. So the accuracy, even though the accuracy is less, the hardware requirement would be very, very small if we do this. So that is how we, because the software model was working good, we actually tried to put it in the hardware model. So this is a purely hardware model where robust time-based ECG slop detection. The first one was published in VDAT 2024. And this one is robust time-based ECG slop detection system utilizing executive neurons, eliminating pre-processing resilience to baseline wonder. This was published in the CAS flagship conference in Spain. And so this, okay, let's skip. Yeah. So here the methodology was use two executive neurons, one for encoding the positive waves and the other one for encoding the negative waves. And then there is a module which detects the slope. Why we went for the slope module is because when the ECG waveform were having baseline wander as well as noise, we found that the detection accuracy was less. So we wanted to create a model or develop the algorithm such that the system is capable of identifying the beats even when there is a problem with the baseline wander or the noise. The noise meaning because most of the noise, because ECG signals are of low frequency nature, the high frequency signal that interferes with ECG is the power frequency. So the 50 hertz and its harmonics. So that is the high frequency for the ECG signal. So the high frequency signal, and sometimes some other artifacts also can come, but majorly these are the two things that will affect the ECG. So we thought that by identifying the slope, we can actually create. So what we did is we did encode the ECG with a pair of executive neurons, and the positive and negative part of ECG are encoded separately, and then we find the time interval between the spikes as the in the spike interval, and slope variation in the ECG signal is extracted. High frequency slope variation indicates noise in ECG, whereas very low frequency slope variation will indicate DC offset and baseline wander. So this proposed method effectively removes both noise and baseline wander and allows for accurate extraction of ECG components. And the work was very novel, and that is why it was published in IEEE Circuits and System Society. IEEE CAS flagship conference. So this is as I said before, the executive neuron has a square law equation in the differential equation. It's a pair of first order differential equation with a square term. So this is the nonlinearity. So these parameters A, B, C, D, etc. were tuned to the encoding process, and these are the values we have used. A is 0.02, 0.2, C is 0.65 minus, D is 0.08, and P is 0.3. And this digital model was implemented in on FPGA, and the spikes we have obtained. So this is a particular ECG signal. We can see that the lot of noise is actually getting mixed with the ECG. So the spikes generated for the positive part of the ECG segment highlighted in the PS1 and PS2. I mean P1 and P2 are this PS1 and PS2. And the spikes generated for the negative wave for the NS1 and then N1 and N2 are given as this NS1 and NS2. So we can, if we identify the slope, the time difference between them, we can actually find the slope between them. So the MIT-based arrhythmia database signals are being used, and the ISA values and the slope variation we had implemented. And this is the logic, the reset, initialization, etc. A fixed number of ISIs are summed up, and difference between every such consecutive sums are determined. And the ISI difference is the absolute difference between the current and the previous window ISI. If this difference exceeds a specific percentage, that is around 25% of the window ISI, it indicates a significant slope. So the significant slope indicates a real ECG wave within that window time. Polarity of the slope is also determined to track the upturn, means ECG is going upwards or downwards. That means a positive wave or the negative wave. Fine tuning the window size and the ISI comparison threshold is crucial for accurate results. And positive and negative channel spikes are processed separately, and their results are combined to get the overall slope. So this is the algorithm what I just mentioned, and this is the result. We can see that this is a particular ECG signal. We have spike for the positive wave. We can see that this is the zero line. Okay, the isoelectric line actually happens here, and the entire wave got shifted downwards because of the DC offset or the electrode problem or the baseline wander. So this is a signal with a negative baseline wander, because ideally this is known as the isoelectric line. I hope you can see this is an isoelectric line. Ideally this should coincide with the zero horizontal line, but it is much lower than that, so that the positive signal, the signal magnitude greater than zero, comes only in the R peak. That is why positive wave spikes come only for the blue, and the negative wave comes everywhere else. Wherever this is missing, this is coming up. And then the system identifies the slope. We can see that the slope change happens only for the duration of the ECG wave. So this region is completely neglected by the system. Why? Because this subtle variation, a small variation of the noise, even though the spikes are generated from the interspike interval difference between the ISI values, the system is capable of identifying that this is not a wave. Similarly, we can see that here the zero wave is here, and this is another wave. We can see that the ECG is, the amplitude is different. You can see the R wave is thinner, QRS complex is thinner here. Here, this QRS is larger. That is a case of bigeminy. And then here, the blue wave represents the R, and the purple is representing the negative waves, and the bottom one is the result. We can see that the slope change signal is clearly identifying the waves PQRST for the ECG signal. Now, if you compare the hardware utilization with respect to LUT, flip-flop, DSP clocks, I/O, and buffers, we can see that the system is much better than existing work. And that the contribution, major contribution, is that existing systems uses a lot of filters, the Butterworth bandpass filter and the reversal system and the aliasing filters, etc., for the processing, whereas we use the direct raw ECG, and that is the biggest advantage of this system. So the raw ECG that can be directly applied, and the system is capable of eliminating high frequency noise as well as the low frequency baseline wander. And then we moved on to detection of atrial flutter detection by ADEX encoded lead to ECG. The ADEX, the flutter is a situation in where the P wave, the actual P wave, will be replaced by flutters. Flutters means a subtle oscillations. So it will not look like P, but there can be 1, 2, or 3, or even 4 flutter waves between two R peaks. That is the condition of atrial flutter. So there are, the P wave normally normally indicates the health condition of the upper chamber of the heart, which is normally, we call it as atrial activity, whereas the lower one is the QRS complex, which we call as the ventricular activity. So this P wave activity normally comes from the upper one. So if there is any delay in the electrification, the potential initiation at the nodes of the heart, that is how the P wave, it goes positive and comes back. There will be a an abnormality in that signal generation. That is how the P becomes as flutter. So what we have done is the presence of sawtooth waves between the RR peaks. That is, so we need to identify the sawtooth wave. So what we thought that because we are able to identify the slope of the ECG signal from the ISI values, we can easily identify the sawtooth, because sawtooth is like a linear wave. So every increment in time, the increment in the amplitude also should be the same. So we can easily find from the ISI values whether that is a sawtooth wave. And then the atrial flutter is a specific case of supraventricular tachycardia where the RR interval will be less than 600 milliseconds. And the atrial cycle length, that means the length from one flutter wave to the other flutter wave in the next cycle, this will be around 180 milliseconds. And individual flutter width can be should be approximately less than 390 milliseconds. This should be greater than 180. And then atrioventricular contraction ratio can be 1, 2, 3. That means 1 P wave, 2 flutter wave, 3 flutter wave, etc. for every R peak. And then regular ventricular response. That means RR interval should be very regular, and the lack of isoelectric baseline. Whereas NSR features means the normal sinus rhythm. NSR represents normal sinus rhythm. All waves, PQRST waves, will be present. RR interval between 600 and 1200. Regular ventricular response and 1:1 AV. That means 1 P wave for every R wave. That is the meaning of 1:1 AV conduction ratio. And presence of isoelectric baseline known as PR and ST. Whereas there it will not be there. So this is a specific case of flutter waves. You can see that these are, very, very minute variation of flutters, but this should be detected by the system. So many systems people have implemented applying frequency domain transformation, etc. And these are all systems implemented previously. They have used, very complex mathematical operation, machine learning techniques, neural networks, etc. to identify that. So all these are previous works. So now, if we infer this, we find that they all rely on frequency domain approaches, and they are unable to precisely detect the occurrence time, because the moment we convert any signal to frequency domain, unless the phase information is properly tracked, we miss the complete time information. So whether these abnormalities has happened at exactly 3:05 a.m. or 3:05 p.m., that would be very difficult to identify if because we take a bunch of signal and convert apply to the frequency domain transformer. But here what happens is that because as the signal comes sequentially in time domain, this encoding process also happens sequentially in time domain. We are able to exactly determine at the location at which this is happening. So the frequency domain techniques are highly complex. Our aim was to develop an SNN classifier which will work with low complexity. So what we have done is the ECG wave with this flutter wave passed through the positive and negative addex neuron. The slope variation module will determine the slope, and it will identify the R peaks. So these are one example of a flutter wave within the ECG. We can see that this is one example where the flutters are very clearly visible. So individual flutter width and atrial cycle length, these are the parameters that will be determined by the system. We also use the same addex neuron for encoding process. So you can see that the same positive spikes and the negative spikes come up, and these negative spikes are because of the flutter waves. And now the system we have built, the algorithm we have developed is this, which will identify the slope variation. So the addex neuron and the ISD and its address is found between every pair of spikes. Then it goes to two slope variation module. The first slope variation module, it finds every spike pair within a window size n1, and then minimum ISD and its address, and then the R peak detection is done based on that. And here for the negative waves, ISD is found for every spike within a window size of n2, minimum ISD and its address. And then flutter width is found by the slope changing direction when it is a consecutive decrease to an increase within one RR interval, or consecutive increase to decrease within another within an RR interval. These 2 points are noted to identify the flutter beginning and end. So this is what I said. I will just go fast here. So the ACL is the sum of the clock intervals between the points where the slope changes from consecutive increase to decrease, whereas IFW is from decrease to increase. And the tachy signal is detected whenever RR is less than 600, because that is the condition specifically for AFL. So then ACL signal is detected when ACL is greater than 180, and IFW is detected when it is less than 390, and atrial flutter is detected when this condition of tachy and the ACL and IFW all are. So a simple are satisfied. So a simple combinational circuit is enough to determine after the features are extracted, these features will be based on these features, the decision block will be working. And this is the output signal that we have obtained for MITBA 04043 signal from the atrial fibrillation database. So we can see that, and this is a, the signal. We can see that the flutter wave present. So these are the flutter waves. We can see that, and they are detected by the system. And here again, we can see that the flutter wave is present everywhere in the cycle, and they have been identified by the system. And then we have compared the hardware implementation with other existing systems, and we find that the proposed system had a sensitivity, specificity, accuracy equal to or better than existing systems. Now we come up to another system. What as I said before, all the abnormalities are being so the previous one was presented in the VLSID conference 2024 and I mean 2025 January, and then we have the hardware implementation of a signal reconstruction system. Why we need a signal reconstruction system is that the entire system that we are building, the abnormality is detected or extracted from the interspike interval. Now, if the interspike interval are not correctly mapping onto the input amplitude, then our system will be incorrect. So what we did was we developed a complete mathematical model to reconstruct the original signal from this encoded spikes. So this paper is about that. This was published in IEEE Nano in 2024, last year. Yeah. So this is hardware implementation of a signal reconstruction system using integrate and fire. The motivation, as I said before, it is important that we reconstruct the original signal from the encoded spike. So this is a fully mathematical model, and the students have developed the complete hardware model for that as well. So this is a simple model of an LIF neuron. A signal with a bias added to that will be continuously integrated, and whenever this integrated value or accumulated value is greater than a threshold del or delta, there is a spike generated. And the moment the spike is generated, it gets reset, and then again the charge will get accumulated. So this is a fundamental model of an LIF neuron model. And this is the signal that we tried to encode. So this composite signal, which we have, I think the expression is here. So this is a composite signal developed in MATLAB by simply putting some, multiple sign signals with different frequency and phase. And this encoded signal has 73 spikes. Okay, so we can see that the interspike intervals here, the amplitude is less, the ISI is larger. Here the amplitude is large, the ISI is shorter. We can see that variation clearly, and these ISIs are being applied to the signal reconstruction system. And finally, we will see the reconstructed signal and the original, this black color signal, whether they are matching and what is the signal to error ratio. So this is the flow chart of the complete signal reconstruction system. The integrate and fire neuron produce the spiking neuron that is applied to the signal reconstruction system. The system identify the spike times as well as the neuron parameters. This neuron parameters specifically will be given to a module near to the output, and the spike times are integrated. It passes through a sync block which was implemented using modified Taylor series. to determine the impulse response of an low pass filter. And this integration module then was passed through a Simpson block for finding the shifted summation of the shifted pulses. And then a pseudo inverse algorithm was implemented using two-sided Jacobi. For implementing two-sided Jacobi, you have orthogonal matrices and diagonal matrix and transpose operation. And then the pseudo inverse operation was obtained by this multiplying three matrices, and then this multiplied by the neuron parameters, we get the weights, and these weights were given to the Taylor series output of the spike train, that is W into H. So here we compute H, I mean W, and here we compute the H, and the product of that ideally gives the series of spikes and the original signal. So this is the mathematical formulation of that. The input signal are encoded, and you get a weighted delayed H of t minus SJA. As you know, this is the weighted, I mean, the delayed impulse sequence of impulse signals. And Taylor series, for the sync function, we used the Taylor series to implement that. And so the pseudo inverse is required because C is a singular matrix, and the SVD function is, this is what I said, using now V transpose has been determined to find the Jacobi matrix. So two-sided Jacobi algorithm has been used. So four elements of a left matrix and the right matrix, and two multipliers only were paired. I mean, we optimized like that, and I would not go through this pseudo code. And then these parameters were computed, and all completely hardware model we have developed, and the number of sweeps, etc., were evaluated, and the codic algorithm has been used to reduce the hardware resources. So the theta and the phi for the sync function was implemented identified using codic algorithm, and these equations have been implemented to determine that. And for sweeping n equal to 50 times, we have swept, and the precision of order of 10 power minus 14 was obtained. And we can see that this is the original. Black is the reconstructed signal, and red is the original signal. We can see that the beginning and the end only the error is small. We can see that the error is much less. And so we get the signal to error ratio 88.0417 dB, which is much less than even the theoretical value in MATLAB. So the system was actually performing excellent manner. And we can find that the model that we use for processing the biophysical signal by encoding it actually is mathematically proved, because the reconstruction signal, the original signal was possible to be reconstructed from the spikes. So we used, the block ramps were not utilized. The total power was on FPGA was 203 milliwatt, and the ASIC implementation is not done for this so far. Yeah. So this is the module-wise representation. So existing system, we can see that it is only 9.34, but they don't use any of these signals. We have all this process completely on board. We can simply feed in the spike, and we get the reconstructed signal back. That is the system. Whereas here all the lookup table, the sync value function, the theta value, phi value, all are used by lookup table. Means one pre-saved data is available. The accuracy also will be less in such cases. So that is how our system was much better than original signal. And then we applied, because we used for ECG, applied this for ECG. We can see that there are some errors in this black line. We can see that some errors are there, but still the error is much less than here. So we got a signal to error ratio of 82.52 dB on FPGA for the ECG record number 105 from MIT. And now we move to EEG. So ECG we have done multiple works on ECG, and then we wanted to work on EEG for sleep stage classification. And the motivation behind that is because in the neural patients in the neural ICU, they are, they normally they may not be able to communicate well based on the severity of the brain injury or the disease. Most probably they may not be in a situation where they can respond to the queries posed by the doctors or the supporting staff, means nurse or technicians. So the neurologist whom we discussed with, they have told us that if we can create an automatic system which will identify the EEG signal, because in the ICU continuously the ECG and the EEG will be monitored, and if we can identify the stage of the sleep in which the patient is in, they will be able to identify whether the sleep is a pathological disorder. Pathological disorder means the patient is really ill, because of that he is in the sleep situation, or is it like, due to lack of, because in the ICU normally the light will be on and a lot of noise will be there or sound will be there, so the sleep will get disturbed because of that reason. So is it like a very very conscious sleep, or is it like a pathological? When I say conscious sleep, what I say is that the patient is really sleeping, or is it like a pathological disorder, because of that the sleep is happening. So that was the question posed to us, whether we will be able to identify that. We have established or validated the system for a normal patient. We are yet to apply it for abnormal cases. So these are the electrodes. Around the 64 electrodes will be placed at different locations of the skull to get the signal. We have particularly used the C4A1, C3A2, and FTZ signals for this analysis. So these are fundamentally the characteristics of the EEG signal. For people who work in frequency domain, they will work on this. There will be band pass filters, different band pass filters with a pass band of 0.5 to 4 to extract delta, 4 to 7 to extract theta, and 8 to 12 for alpha, 13 to 30 for beta, and greater than 30 for gamma. And then this amplitude of each of the signal will be identified, and based on that, the particular sleep state will be determined. And normally a healthy person, when it goes to the sleep stage, the awake stage is the when we are awake, and the sleep stage actually have non NREM represents non-rapid eye movement. REM represents rapid eye movement. So a rapid eye movement is a very deep sleep, and NREM is not that deep sleep. So NREM, this is the time where we see what do you call dreams. So this is a 90-minute cycle. So this 90-minute cycle, around 5 to 6 times, it will be repeated during a 6-hour sleep for us normally. 6 to 8 hours sleep. So that is how normally the cycle comes. So here also what we did was we used the EEG signal, used ADEX to encode that, and then we extracted the statistical features from that, and then the statistical features we applied to a machine learning model and on MATLAB, and then classified the different stages of sleep. So the methodology is that we extract the different parameters. So we can see that this is the EEG signal. Again, we use the same concept, the ADEX neuron for encoding this for ECG, the positive and the negative. And this is the zoom view of the spikes that are generated. And then these are the parameters that we have used. The Hijort is a scientist around 1960s. He had proposed 3 parameters known as Hijort activity, mobility, and complexity. These specific parameters, given by these equations, the variance, the root of the first derivative to the variance, and then the second derivative to variance, the activity. So these 3 parameters we have used. Then the statistical parameters, mean, median, first, third, quartile, interquartile range, and another parameter is called ZCR and SUM also. The CSDM also we have applied. So then we analyzed the deviation, the mean values in each of the sleep. So W represents wake, S1, S2, S3 represents S4 represents 3 stages of sleep. And according to AIS1 standard, S3 and S4 together are combined in the single sleep, that is called the slow wave sleep, SWS. And R is known as the REM, which is the dream sleep. And all statistical parameters we have analyzed and done compared their performances, and found the how different or how closely matching they are, so that we will identify which characteristic will determine will be able to help us in identifying a particular stage of sleep. So the observation that we got was Hidol's parameters activity increases in stage 3 and 4 but decreases in other stages, and mobility also increases in WS1 and S2 but decreases in other. Similarly, complexity and variation in ISD, and then inference was that ISD is inversely related to EG amplitude, and whereas mobility it is directly related, and complexity it is inversely related because of the second derivative and the input amplitude. So based on this, we found that the relative values wake and RUM, we get the relative values lowest, and the stage 1 higher than wake and RUM, stage 2 between wake and stage 1, and stage 3 and 4 highest. So based on that, each sleep stage can be differentiated, but wake and RUM stages are difficult to differentiate. Then we thought about, what is our additional parameter we can identify, and then we came up with the zero crossing point or zero crossing distance. So when the positive spikes from the positive signal comes up, we identify that there is a positive wave detected. Similarly for negative wave, and accordingly we find that we developed an FSM to identify the positive and negative signals from the ISI values. And we found that this was a good observation that we got. For an epoch duration, we can see that the zero crossing values clearly distinct in each of the stages. We can see that 130, 160, 93, 73, 39, 64, etc. So based on the we have decided to go for 10-second epochs for the process, because there was clear distinction between the zero crossing values in each of the stages. So that is how this is the result of the zero crossing stages. We identified this for a different EEG record, stage 1, different stages also we have done. And then I will continue the result after some time, the updated result that we recently published in the ITK Journal of Biomedical and Health Informatics. And then this is another work that we have done for lead to ECG without any filters and pre-processing. This was done in the Prime conference in 2025 in the September. My PhD scholar went and presented there. It was in Italy. And let us come to this. We show the ECG signals, the L beat, the D beat, the N beat, etc. So these are the, we can see that these beats are, very difficult to distinguish. So the system should be capable of identifying these characteristics. So N represents the normal, S is supraventricular premature beat, this one, and V is ventricular premature contraction, L is left bundle branch clog and right bundle branch clog, and atrial premature beat. These are the different beats that we need to identify. So, and then we have the bijourney, trijourney situations that comes up within the signal, and then ventricular tachycardia. So we see that the morphology, not only the amplitude, morphology of the ECG signal also to be identified to detect a particular case of arrhythmia. So that is how next we developed the system. So I'll skip this literature survey, different systems people have used. So next we developed a system which will identify or detect the ECG signal from the slope identification, and it will detect any case of arrhythmia the system is capable of identifying. So the ECG is scaled down by a factor of 100, and offset of 60 to 80 microvolt has been added as an offset, and it shifts the signal well above the zero baseline. and then it enables the threshold spike detection to preserve the spectral characteristic and morphology and integrity of the ECG. We can see that this is a MITBH51 signal, and if this is the case of two R peaks, this system is here. You can see that a dense spikes here also a dense spikes. So this is an L beat, which is identifiable by the system. So this is the ADEX neuron. So this RP detection system, the ADEX inherently functions as a low-pass filter. Its membrane dynamics perform temporal smoothing, and then exponential term enhances rapid transients and suppress slow drifts like baseline wander. As a high-pass filter, adaptation current W, it characterizes as a high-pass, and QRS and RP directly from raw ECG signal without any pre-processing. So this two FSM have been developed by the student, and these two FSMs were capable of identifying. So del I represents the current ISI, the interspike interval. Del I minus 1 represents the previous one. So if the current I del I is greater than the previous one, it stays here. Whereas if it is less than, that means it is an upward signal. So because as the signal amplitude increases, the ISI value will decrease. So if there is a decrease in the ISI value, that means the signal is going up. So accordingly, the system will identify whether this is an upward slope or negative, coming down signal. So system, so there are counters set up for identifying the total ISI value for a positive slope as well as the negative slope, and it will identify the positive half wave and negative half wave distance. So exactly the morphology of the signal can be identified. So this is the signal that it's a ventricular couplet that the signal is there. So we can see that a steep rise in ISI count is happening. So this steepness, we are able to determine the steepness of ISI. For example, here we can see that this is a steep curve, whereas this is a ramp type curve. So the system will be capable of identifying whether the steepness is there or not. In the case, if you compare these two, this will come like this. And the steep rise in the del low, mid, etc. Del low represent the initial count, del low, del mid will be the middle count, etc. The system is capable of identifying this, and the result obtained for different waveforms might be age 101 and 105. We can see that this is the system. You can see that it is subjected to severe baseline wander, but these green dots represents whether the system has identified these R peaks. We can see that everywhere, even in the presence of high frequency noise or baseline wander, the system is identifying these R peaks. And here we can see that high amplitude noise with artifacts. We can see that red dots are there. Red dots means they are false positive. They are identified as R peaks, but they are not R peak, they are noise. So the system, sometimes it identifies, the accuracy is, any system that we develop, definitely accuracy will not be 100%. But, we wanted to show that in certain cases, the system may not be able to identify. That means when the noise amplitude is equivalent to an R peak, and if it comes within one RR interval. Why? Because we have programmed the system in such a way that once an R peak will be detected, there will be a blanking period. After that, only the next R peak will be determined. But here it happens that they are closer. The noise comes closer. So it was, especially in the case of doublet, it was undetected. Similarly, for the noisy ECG signals also might be at 203. We can see that the system is capable of detecting. And then another record, 222, there are motion artifacts. These artifacts are labeled by the MITBIH. So we have specifically chosen such signals where some artifacts have been mentioned, and then we applied the technique to those signals to identify whether the system is capable of identifying. And then we can see the beats here. These are the record numbers 105, 106 up to 233. The total number of beats is from 2000 to 3000, and we can see the false positive, false negative, and the total count. This is for the reference work, and we can see that the proposed system. We can see that our system works much better than existing systems. And we have also compared with the other biogas, conference papers, and we found that they have used pre-processing, whereas where we apply directly raw ECG, the technology node is 45 nanometer, area was much less. Definitely technology node is less than, means area will be less, and the power is 0.38 micron, frequency was 1 kilohertz, methodology was the slope from ISI, and the analog front end was required for them, but we don't need an analog front end. And arrhythmia peaks, they have used other types of arrhythmia. We have in this paper, we have used only R peak and RR detection, and then noise robustness, baseline wonder, other types of interference artifacts, high frequency, etc. Everything the system is capable of identifying, and we have tried all 48 records from the MIT PI. So the proposed system is capable of identifying them. And this is the work that recently got published in the Journal of Biomedical and Health Informatics. And this is work on identifying the sleep stage, in neuromorphic time domain EEG classification framework using ISI from ADEX encoding and OPC4A1 signals. So this is we named the system as Sleep ISI. So Asha and Vasanthi are PhD scholars. Sapna is a neurologist in the Sri Chitra Tirunal Institute of Medical Science and Technology under Department of Science and Technology located in Kerala, Trivandrum. And Kalpana and myself, we are, the faculty members at IIT. Yeah, so I will skip this sleep. So this is the electrode placement. Basically, we have worked on this is C4 with respect to A1. C4 is the central electrode, and A1 is the earlobe electrode, and then C3 with reference to A2. C3 is on the left side central electrode, and with respect to the right earlobe A2. And then we have FZ and PZ means F. This is the Z electrode. Z orientation, F with respect to P along the Z. So these are the three signals we have utilized, or we have now, taken from the different databases. We have used three different databases to identify the sleep complexity. So as I said before, assessing sleep staging is critical in this. The practical challenge is that manual scoring is a manual scoring means a person will go near the patient in the ICU. He will have a chart known as Glasgow chart, and with the chart, there will be some questionnaire in the chart. He will show the finger with one or two numbers and ask the patient to answer with the eye movement. He will say 1 means you open the eye, 2 means you close the eye, something like that, and the patient will respond to that. So this is like a crude method. Because there is an automatic system is not available, people rely on such systems to identify the response of the patient. And once the doctor comes for rounds, the doctor will look at the what is that? Doctor will look at the how do I say, the chart, and based on the technician's perspective, he would have given like poor, satisfactory, moderate, good, excellent, like that. So based on the ticks that he puts on the chart, the doctor will come up with a conclusion. Okay, the medicine is working or the medicine is not working. So based on that, he will change the course of medication. So that is what the doctor said, that it is necessary that we develop an autonomous system which can identify. Just I wanted to show the 21 electrode EEG signal. So this is the type of EEG signal that we have to process. So a standalone, the aim is that a standalone low power time domain sleep stage classification system that supports neurologists through real-time EEG interpretation. This is our aim to develop that. So these are the different JBHI papers that have come, a feature fusion model based on temporal convolution network for automatic sleep staging using single channel EEG, and then a modality specific feature selection, data augmentation, and temporal context for improved performance. And another one, all are the BHI papers, EEG based sleep stage classification via neural net architecture. And then this is the the Naladambi's paper there, where the ECG was used for the neuron encoding, where he has used an LA of neuron, whereas we used an ADEX neuron. And then a graph temporal used the dual input convolutional neural network for detecting sleep traces from EEG. And another one again, EEG classification. These are all TB-CAS papers. And then what we found the research gap is that dependence on pre-processing and frequency domain analysis was required, which will be very complex computational requirements. And so the feature extraction, computation, classification with ANN. So this will need huge hardware and memory. So the lack of ASIC and FPGA implementation was also there. So accordingly, we wanted to develop a pre-processing free time domain framework known as Sleep ISI that encodes single channel EEG into spike trains using the ADEX neuron model for determining the sleep stages efficiently, accurately, and in a hardware friendly manner on real time. So the objectives was to encode the EEG signals using the ADEX neuron and optimize the encoding process for improved spike-based feature extraction. And then once the spikes are encoded or the signals are encoded, use the spike to determine the inter-spike interval and determine different time domain features from this inter-spike interval. So then to determine the discriminability feature of the statistical parameters using critical values test and done post hoc test. So this, we found that the variation of the ISI do not follow normal distribution because this KW test is applicable only when the data doesn't follow normal distribution. Sometimes, in random probabilistic situations, when the data is following a normal distribution, we cannot apply crystal. Then only then we should not apply crystal value. So in our case, it was not following the normal distribution. So we can apply KW test and done test. So we did this test and then we developed a hierarchical classification model with a 5-fold cross-validation to accurately differentiate the stages of sleep. And so this is our complete system, the current developed system. So the EEG, we identify the digital version of the EEG downloaded from the database. MSB is identified as positive or negative, and then MSB 0 means we directly encode it. If MSB is 1, we invert the signal and again encode it. So a single ADEX neuron was able to encode both positive and negative waves. And then these waves, positive and negative waves, are processed for positive spikes and negative spikes for ISI are determined. And from this ISI, we calculate different parameters, mean, median, Q1 means interquartile range, Q1, Q3, and ZCR, CSDM, cumulative sum of deviation from the mean, and CSDM of each of the parameters. And then we applied the on MATLAB. So this much is hardware. Up to here it is hardware. This much till the extraction of parameters. But this one is in software model. It is in MATLAB. That we apply a hierarchy level random ensemble model, which is random forest model, for identifying the stages of the sleep. So the first level in the hierarchy model, first level, it will identify whether it is a sleep or a wake. And then this is again applied because we found that within the wake, both S1 and wake were there. So we split here between the second level, it will split between S1 and wake. And then this sleep signal is again given here. S1, S2 REM and SWS were split. And then this S1, S2 again given for the level 4. It will identify S1, S2 and REM. And then you have S1, S2 separator. So this is S1 and this also is S1. So that is how we identify the different systems. So now this is the summary of the data set that we have used. The MIT BAH CAP database, C4A1 and C3A2. There were 12 subjects with a different sampling frequency, 512 Hertz, 100 Hertz and 200 Hertz. And the total samples were around 12,000. Among which the labeled data, it showed like, the wake S1, S2, slow wave sleep, which is S3, S4, and the REM, high amplitude signal. And the CAP also had C3A24 records sampled at 128, which also had these many samples. Then we worked on, because the reviewers asked for cross validation across data sets. So we took the second data sets ISRUC S3, which had 20 records of each C4A1, and this was, a sampling frequency 200 records. And then we had sleep EDF 20, FPZ CEZ, and that also was, 20 records were there. So this is the signal after encoding. We can see that the variation of ISI as well as the spike count, if you see, the variation is very clear. So this is the noisy EEG signal. If you see the rate at which the spike count means the spike rate, count of spikes that are generated, we can see that in a 150 nanosecond window, we can see that it actually maps or matches with the EEG variation. And whereas ISI will be inverse of that, when this is maximum, ISI will be minimum. So inversely, so encoding of positive and negative part of EEG with ADEX showing ISI variation with the EEG amplitude. So the same ADEX neuron was used, and then we did the statistical parameters were done, and they have been sorted with the ISI values which were developed, delta 1, delta 5. So this is how the spikes would be received. I mean, the interspike interval would be evaluated, but then it is required to be sorted. So the sorting model will arrange them in the ascending order. Once it is arranged in ascending order, computing Q1, Q3, Q1, Q2, Q3, IQR is very easy, and then we can directly find the mean also. So the mean is found from average of all ISIs, and the Q1 is found where at 25%, 75% is Q3, and 50% is Q2, which is median. And the spread of the central 50% is known as the IQR, which is Q3 minus Q1. And then the zero crossing rate, as I already told at the beginning, this FSM, the same as FSM, will identify the zero crossing, and this is the output of that. And then we found the Hijorth parameters. So the Hijorth parameters, what we did is you need to find the first derivative. To find the first derivative, we find the slope difference. The second derivative, we find the slope of slope, means twice V2. And then we find the CSDM cumulative sum of deviation from the mean, and that is how we find the CSDM activity, mobility, and complexity. So, and all features were computed for 10-second window because we wanted to minimize the hardware, and that is averaged across 3 consecutive 10-second segments to obtain the 30-second values. And these are the results obtained. So ISI features not follow a normal distribution. So these are the values of the mean, and you can see that, and these are the count of zero crossing. This is the CSDM of del mean and the CSDM of activity. We can see that a clear distinction is there. Crystal values test was conducted to assess the statistical significance, applying a threshold of less than 0.01. Get done post for pairwise stage comparison. So this is the result that we have got. You can see that the one is mean. Okay, it is not visible here. Yeah, up to P10, there are 10 parameters here, all 10 parameters. So this actually 1 to 10 represents the 10 parameters to identify the wake. So wake versus wake, all 10 parameters were useful, whereas wake versus SWS, the sixth parameter, that is Q1, was not significant. So green is representing the done test. P parameter is, the crystal values P parameter for the pairwise test. P is less than 0.01, and blue represents less than 0.05, and red represents less. This is between 0.01 and 0.05, whereas this is 0.0 greater than 0.01. So we have, based on the green values that are coming up, we have identified wherever the discriminability is there, and those parameters have been used in the 4-level hierarchy model. So this is a progressive feature augmentation. In the level 1, we have the sleep versus wake. All the parameters have been used in every level to identify the specific case of the sleep stage. And first we used only 3 parameters, which is known as mean, zero crossing rate, and CSDM. Then we augmented it with the 7 parameters, adding median, IQR, Q1, and Q3. And then we added the 10 parameter model, CSDM activity, mobility, and complexity. And this was giving the the best hardware performance. So we can see that accuracy is on the left side, and the right side is L1 represents wake versus sleep, L2 represents slow wake sleep versus S1 S2 REM, and L2B represents that also level 2 wake versus S1, L3 represents REM versus S1 S2, and this is SWS versus S1, this in the L4. So we can see that this 3 parameter, 7 parameter, 10 parameter, the 10 parameter ideally improves the accuracy. We can see that for level 1 96, level 2 94, level 2B 98, level 3 87, and level 4 82.69. That is the final accuracy. And this is the heat map. You can see that heat map, the hypnogram, predicted versus actual hypnogram for 500 epochs of cap N11 for 3P, 7P, and 10P features. So this is for 3P predicted and actual. This is 7P and this is 9P. We can see that the system more or less are the same. There are some, here there is some problem, here there is some problem. Remaining everywhere, it is nearly equal, the system. So this is the accuracy and macro F1 score improved from 3 to 10 features. What is the variation? We can see that this is DB1 represents database 1, DB2A represents the second database, and 2A, 2B represents two records, C3, A2 and C4A1, and DB3 is the third database. We can see that the accuracy and macro F1 score, this is for accuracy, this side, and this side is macro F1 score, improves as the feature size, the increases. And here the classification accuracy of different ML models, decision tree, KNN, naive Bayes, RF, and SPM. These models, besides, as I said before, this we have not implemented on hardware. It is a MATLAB model. We can see that the RF model, the pink one, was better in every case, and that is how we decided to go with. And this is the comparison with the existing model. We can see that all the existing model, they have used different types of neural network as well as different types of pre-processing, and some are time domain, some are frequency domain, some are time frequency domain, and these are the accuracy values they have obtained. So whereas our model without neural network, the raw cap database and the ISREC database, and we can see that our system is much better than comparable or better than the existing ones in terms of all the overall parameters, like overall metrics is accuracy, macro F1 score, and kappa, and F1 score per class for each wake, stage 1, stage 2, S3, S4, and REM. And then we also compared the hardware performance, area power, and cell count results from Cadence DNS with 45 nanometer PDK for extracting 10P features from ISI for 10 seconds and 30 seconds epochs. We can see that this is 10-second and this is 30-second direct computation. We find that 30-second direct computation is slightly larger than the 10-second. So that is why we developed the system for evaluating the parameters for 10 seconds, and 30 seconds is found by averaging out for 3 consecutive 10 seconds. And this is accuracy versus number of splits for CAP, ISREC, S3 for the RF tree. We can see that as the number of splits are increased from 50 to 100, we decided to go with the 70 to 80 splits, because beyond 80 there is not much increase, it is almost saturated. So we decided to go with that. So this the summary is that the sleep ISI and neuromorphic time domain ISI framework for eliminates pre-processing, segmentation, frequency domain, and statistical features validated on multiple data sets, and hardware implementation for feature extraction, and that is neuromorphic at pre-processing free EEG and cross dataset generalization up to 92% accuracy, and ASIC verified hardware feasibility at 7D microwatt. But the performance of stage 1 need to be improved. We have applied only to healthy subjects. We have not worked on disorder cases. The next aim is to apply this technique for disorder cases and aim better deployment in this. So these are the references. So this I will skip because this is not relevant to. So these are the papers only last year I have included here. I thank all my students for doing this work. Thank you for this opportunity.
Thank you, ma'am.
Yeah.
Participants, if you have any doubt, you can unmute yourself and ask, or you can post it in the chat box too.
Okay, I will stop sharing.
Okay, ma'am. One minute. Uh, Thank you so much, ma'am, for accepting the invitation and sharing your expertise. Now, I invite Ms. Sandra here to deliver the vote of thanks for the session of day two. Over to Sandra.
Good evening, everyone. It's my privilege to deliver the vote of thanks for this enlightening session. On behalf of R.M.D. Engineering College and Department of ECE, I extend our sincere gratitude to Professor Binsu Kailath, Professor and Dean, Indian Institute of Information Technology, Design and Manufacturing, Kancheepuram, for sharing her valuable insights during the session on Introduction to Neuromorphic Circuits and its applications. Ma'am, your detailed discussion on recent research trends, publications, and ongoing studies in neurophonics and healthcare system has truly inspired the participants to explore new direction in their own research work. Thank you, ma'am, for taking the time to share your expertise and for encouraging us towards impactful research-oriented innovation. Thank you, ma'am.